This is the lecture for Chapter 3, Part 2. We're going to go clearly over the correlation formula to make sure that you understand it. So let's start with Pearson correlation and how to calculate it so that we can determine the direction and strength of the linear correlation. So what do we need? To calculate the correlation coefficient, you need the scores for two variables, the mean for each variable, the standard deviation for each variable, and a z-score for each raw score, for each person and for each variable. We're going to go through this step by step. You're going to start with your data set. Here we have my data set that I like to start with, and I started talking about this in the previous lecture in part 1, and I realized that I had one of my formulas wrong on the next slide, so I wanted to stop and correct that. So here we go. We're going to start with our data set. We have the column for N, which is the number of our participants. We have a column for our sleep data and a column for our mood data. And so remember, we use Excel or some other spreadsheet to do our calculations for us. There's no sense in using your calculator. It's very tedious and time consuming, and it promotes making mistakes. So here I show you that we've already created a scatter diagram. Excel created this for me, and we can see it looks like we have a positive correlation going forward. So we'll see how this works. If this is accurate. I mean, it is accurate. It's just we'll see if our guess is correct and how strong the correlation is. Okay, so we're going to do our calculations. And this is the formula that I didn't have here for you. I wanted you to see the standard deviation formula. So I have separated the data for sleep and for mood. What I did is I just copied the data onto another tab for sleep and for mood. Notice that I keep the ends with the data so that they're not separated from their people, so that the scores remain with the participant number, so that we keep them in sync with each other, since we are going to correlate them by the individual. Okay, but now we're going to calculate some things. We're going to get the deviation, which is just the score minus the mean. So it would be 5 minus the mean, which is 7 here for sleep. And so we have 5 minus 7, 7 minus 7, etc., all the way down. We've calculated our means. We've calculated our deviations. Notice that the sum for the deviations is 0 because they are all equally apart from the mean. And then we're going to square each of the deviations. So the formula for squaring the deviation is, because we have the x minus m right here, we would just take this cell right here and square it. So you would mark your formula in Excel, usually with a little caret. A caret is a thing that looks like this with a 2. Okay, so you would have your cell here, your cell here. Like say this is cell C2. Yeah, it's really hard to write on this, but you would use this caret and a 2. I've got another slide. I think I go into it a little bit more detail, but I just wanted to make sure you can see that we are using Excel and we're using the proper formulas. But you can see here that the square for each one, -2 squared is 4, 0 squared is 0, etc. So we have the data for sleep and we have the data for mood. The next thing, once we have the standard deviations for each of them, we're going to sum them. The sum is 16, and we're going to get the variance. So I've included here the calculation for variance, which is the sum of the squared deviations divided by n. Okay, so we have the n here is 6. So this number right here, the 2.667, the formula to achieve that is just this cell, which is 16, divided by 6, and you get 2.667. In order to then get the standard deviation, which is what we need to calculate the z-score, the standard deviation is just the square root of the variance. So in this small table right here, I've calculated all of the things I need to get the z-scores for each of these individuals for sleep, and then again for mood. So the variance for mood is 3.667. The standard deviation is the square root of that, which is 1.915. Okay, so we've made these calculations in Excel, and they're done for us. You still have to make sure you put the cells and the formulas in the right place, but you can do these with a calculator. I just want to make sure that you are able to see your work clearly, so you know if you make a mistake, where the mistake was made. Okay. So now you're going to calculate your z-scores, and this is where I add a column in that same Excel spreadsheet. So I have mood here and sleep, so I moved mood to the top and sleep to the bottom, and we put the column for the z-scores. Now to calculate the z-score, we have mood, or what I mean is the score, so x, which would be here, it would be y, but the score minus the mean, and the mean is here, okay, divided by the standard deviation. And so I would just write this formula here in the z column. So each of these would be this cell minus mean, which is 4. I wouldn't put this cell, I would just put 4. So I would put this cell minus 4. Okay, so it's the score minus the mean divided by 1.915. Okay, so for each one of these, you get the z-score for each person for mood, and then their z-score for sleep. And you see that they're different because their scores were different because the means were different. So they have different scores for each one. Okay? So in Excel, the squared deviation is typed as the cell for the deviation, which is right here. This is the deviation cell, okay, with the caret and the 2, or you can just multiply it by itself. Okay? All right, so now we've calculated our z-scores. We have the elements that we need to calculate our Pearson correlation coefficient. All right, so here's the formula. R equals the sum of the product of the z-scores for x and for y for each individual, all added together and divided by the number of participants. So we have 6 participants. We have the sleep z-scores. We have the mood z-scores, and we just multiply them going across. So negative 1.22 times negative 1.04 is positive 1.28. 0 times 0 is 0. 0.61 times 1.57 is 0.96, etc. So you can see these going all the way across. So you calculate each cross product for the 2 variables per participant, okay? And then you add the cross products together right here at the bottom. We've got the sum. And then you divide this sum by n. And the n is the number of people we have, which is 6. So 5.12 divided by 6 is 0.85. Our R is positive 0.85. Sometimes you'll see it just positive 0.85. Okay? Now, what patterns do you notice about these z-scores? One of the things that I notice about them, and perhaps you noticed them too, that when the z-score for sleep was negative, it was also negative for mood. When it was positive, it was also positive for mood, positive for sleep, positive for mood, negative for sleep, negative for mood, etc. Do you see that? This pattern, as you notice, of course, we only have 6 participants, so it's easy to notice. When you have 1,000, it's going to be a little harder to notice. But what you notice is that they are negative together and positive together. So we do see a positive correlation. So now we have our correlation coefficient. Now, what does that mean? What does it mean? The Pearson correlation coefficient gives the exact correlation between the 2 variables. The direction of the relationship is told to you by the sign of the correlation. When we have the plus sign, it is a positive correlation. When we have the negative sign or the minus sign, it is a negative correlation. So the R tells you the general trend of the relationship between the two variables. Okay, so first it tells us the direction, and then it also tells us the strength of the relationship. So the value of the R ranges from 0 to 1. It actually will range from -1 to +1, okay? The value of the R, if we're just thinking about not the negative or the positive, but we're thinking about just that value, it's going to be from 0 to 1, okay? Back in our early math classes, we called it the absolute value. We don't really see that a lot here, but that's what we're talking about. So the value of the correlation defines the strength of the correlation regardless of the sign, okay? So even though negative 0.99, even though it's negative, it is a stronger correlation than positive 0.75 because it is closer to the absolute value of 1. 1 is the highest value a correlation can have. Correlations of +1 or -1 means that the variables are perfectly correlated, and a correlation of 0 means that they are not correlated at all. Okay? Now, generally speaking, we've gotten a range here from our book that tells us that plus or minus 0.1 or 0.10, if you want to call it that, is a small association. 0.3 is a medium association. And it looks like 0.5 is a large association. I've seen it at 0.7, but obviously that would be a larger association. But we're looking for the larger the number here, the stronger the relationship between the two variables. So this tells us that the relationship between numbers of hours of sleep and mood is a positive, strong correlation, okay? Now, just to go over those steps, you change all the scores to z-scores. You figure the mean and the standard deviation for each variable. You change each raw score to a z-score. You calculate the cross product of the z-scores for each person. You multiply each person's z-score on one variable by his or her z-score on the other variable. And then you add up those cross products of the z-scores and divide by the number of people in the study. And that is how you figure the correlation coefficient with this formula right here, okay? Now, we were talking about the direction of the relationship, but now let's talk about the direction of causality. When we first were talking about the way you would do the axes on your graph, when you would draw your graph and you draw your axes, and I told you that we tend to put X as the one that predicts Y, okay? But sometimes we don't really know when we're getting started. We can just randomly pick one as X and the other as Y because we don't know what the relationship is. And sometimes we see maybe it is that X causes Y, but maybe Y causes X. Or maybe there's a third variable that causes both variable X and Y. So what happens is, even though we see that they are strongly related to each other because they are correlated, we cannot determine which one causes the other or if there's even a causation between the two, okay? So I found this website. I'll post it in our class, and I've posted it in our discussion board for Unit 2. This is, for an example of what we call a spurious correlation, which is a fake correlation. These two items are strongly correlated with each other, okay? The divorce rate in Maine and the per capita consumption of margarine, okay? Now, do we think that eating margarine causes the divorce rate to go up or down in Maine? Or does the divorce rate in Maine cause people to consume more or less margarine? I don't think either of those cause the other, but we do see that they are strongly correlated and they follow the same trends. I just thought this was a great website. You'll see more of this when we get to discussion board for Unit 2. So there are some things you can do to rule out the possible directions of causality so that you can figure out what is causing what, okay? And one of the things that you would do, or two of the things you can do, is to do a longitudinal study where you study people at 2 or more points in time, or you could do a true experiment where people are randomly assigned to a particular level of a variable and then measured on another variable. So these are some ways that you can rule out causality, but it takes a lot of work and it takes some time to do that. So sometimes what will happen is your result of a correlation will give you ideas for how to take your research to the next level, okay? So there's a couple more things we need to talk about. We were talking about how we can predict one variable to another, but how do I know that the correlation is not just based on chance? So we call this statistical significance. How do you know the result wasn't just based on chance? If the probability, which we'll call small p or just p, is less than some small degree of probability, for example 5% or 1%, the correlation is considered statistically significant. And we will talk about this later on, especially when we start to do analysis of variance, and we will talk about that probably more in chapter 8, but we will probably touch on it in the next few chapters as well. So just keep that in mind, statistical significance. So let's talk about what we can do with R. Now we have this number. It tells us the strength and the direction of the relationship, but when we square it, it tells us even more. And so that's one of the things that we'll often do is we will square the R, and we can compare correlations with other variables. We can show how much of the proportion of the total variance in one variable that can be explained by the other variable. So in this example, we have our sleep and mood correlation right here. When we square that, we get 0.72, okay? Remember that these are all going to be less than 1, and once it is squared, it also loses its sign, so it's still going to be positive. But what this tells us is that the relationship between sleep and mood, 72% of the variance in mood can be explained by the hours slept. Now, I did point out that this was fictional data. This was not data that was based on an actual experiment that was done by the researchers in our book, but it is similar to research that has been done. It's just not exact, okay? But according to this data, 72% of variance in mood can be explained by the hours slept, okay? So now you start to see the power of the information that you're getting from this correlation coefficient. It's not just the strength and direction of the relationship, but with a certain amount of confidence, you can say how much the relationship and how much one variable can be explained by the other, which is kind of like prediction, isn't it? So let's talk about this prediction. When we are talking about prediction, we're not talking about using a crystal ball to predict some future event, okay? I would love to be able to predict things and make a lot of money off of predicting lottery numbers or race winnings or football winnings, okay? But what we can do is we can predict certain variables by looking at the relationships they have with other variables, okay? So for example, we have level of education can predict how much income you might have later on. Your SAT scores can predict your college GPA. Okay, so the X variable can predict the Y variable. So we call that the predictor variable and the criterion variable. Okay, so the variable being predicted from and the variable being predicted to. So we are predicting from your SAT scores to your college GPA. This becomes the criterion variable. Okay, so let's talk about how we would do that. There is a formula for it, and it starts to get really complicated in our textbook. Okay? When we talk about making predictions from a correlation coefficient, we also call this regression. And from a predictor score, you would determine the standardized regression coefficient, which is another word for beta. This is what they call beta. It's got this B with a little line underneath it. It's a Greek letter. You multiply the standardized regression coefficient by the person's z-score on the predictor variable. So the predictor variable would be, for example, in this one, let's say that beta is 0.30. Their z-score is 2 on whatever variable we want to call it. Call it their high school GPA, for example. This is just an example that was given in numbers. I don't know what the real life example might be. But when there is only one predictor, the variable beta right here, when there's only one predictor variable, that comma doesn't belong there. So you can cross that out. When there's only one predictor variable, the beta is R. Okay, so that's one of the things our book took several pages to tell us, but beta is R. Okay, so we already have our R from our mood and sleep correlation that we created. This is an example of how to calculate that. It's very simple. It's your B, or your beta, I mean, and which could be R, and it's multiplied by your predictor variable score, your z-score. Okay. If you need to do this with raw scores, you would convert the raw scores to a z-score in order to fit it into your prediction formula. Okay. Now, in research articles, one of the things that you'll see, you might see scatter diagrams. You will often see correlation coefficients, and sometimes what they'll do is they will put a table that has a whole correlation matrix, which is every correlation in every variable correlated with the other variables. So here's 1, 2, 3, 4, 5, 6, 7 going down, and rather than put the words going all the way across, they just put 1, 2, 3, 4, 5, 6, 7 going across. So this would be avoidance withdrawal, and correlated with avoidance withdrawal, notice it's a 1 and a 1 and a 1 and a 1 going all the way down, because they are going to be perfectly correlated with themselves. They're also going to do the correlation matrix only in 1/2, because the other half would be exactly the same. Okay, so these are the correlations between positive tone and self-blame. Okay, I need my glasses, huh? Okay, let's look at that. Yeah, positive tone and self-blame with avoidance and withdrawal is a small correlation. We have open confrontation with avoidance withdrawal, small correlation. We have cost escalation with avoidance withdrawal. It is a large correlation, and one of the things you can see with it is that it is, this is the probability significance right here. The significance level for the ones with the double stars is a 0.01. It means there is less than 1% chance that this relationship is due to chance. And this, when it's 0.05, it's less than 5% chance. It is less than 5% chance that the relationship is due to chance. Okay. So I know that this is a lot of detail to put into one little chart, but sometimes when you're looking through research articles, you will see a correlation matrix just like this, and it'll show you how all of the different variables are related to each other. Okay, I'm going to stop here. Our book continues on with multiple regression, and I'm not going to test you on that, so I'm going to stop here. Please email me if you have any questions at all. Thank you.